In this video, we're going to continue with solving limits analytically, and we're going to discuss something called the squeeze theorem, which is also known as the sandwich theorem. But I'm going to be using the terminology squeeze theorem in this class. So what is that? What is the squeeze theorem? Well, it says that if f of x is equal or less than g of x, which is equal or less than h of x, when x is near a, and I'll say what a is in a second, but as long as this is true when x is near a, except possibly at a itself, and we have a second condition here, and we know the limit as x approaches a of f of x, so this smallest function, is equal to the limit as x approaches a of h of x. So if the two limits are equal on the smaller function and the larger function at this value a, and that is some limit which we'll call L, then the limit as x approaches a of g of x, so the middle function, must also be L. Well, let's draw a picture to make sure we understand what all of that means. All right, so let's have a picture here where we have some function h of x, and we have some function g of x, f of x here. And we have some function g of x that ranges in between these two everywhere. Okay, so this picture satisfies what we have up here. F of x is equal, bring this down. F of x is equal or less than g of x is equal or less than h of x. So g of x is between f of x and h of x everywhere, near some value a. So this is the x value a. And the height here, the y value, is some value L. So we know that the limit as x approaches a of f of x is L, and the limit as x approaches a of h of x is L as well. So those two limits are equal here. Well, then the middle function must also limit to that value. And that's what this theorem says. So, how can we use that? Well, that's actually quite a powerful tool for several proofs in calculus, but also let's just look at trying to prove a particular limit here. So we're going to prove the limit as x approaches 0 of sine of x over x is equal to 1. To do that, we're going to need to draw a picture, and we're not going to talk about limits yet. We're just going to draw a picture and talk about some trigonometry first. So let's look at an angle theta within the first quadrant of the unit circle. So our radius here is 1. We have some angle theta here. Well, what is this point right here? This is the point cosine of theta, comma, sine of theta. All right, that's our x and y value, given some theta in the first quadrant on a unit circle. What is this point right here? Well, that is 1 comma tangent theta. Let's verify that real quick. This is the opposite side of this angle theta on this triangle. And what do we know? We know that tangent of theta is equal to opposite over adjacent. But the adjacent side is 1. So the opposite is just tan theta, and the opposite here is our y value of this particular coordinate. So the opposite is tan theta, i.e. the y value is tangent of theta. Okay. So if we have that information, let's write out a couple of other things. I'm going to draw a picture, several pictures here. So this is one, this is tangent of theta. We have our sector here, and this angle here is theta. Then we have the area of the triangle. What is that? Well, that area of that triangle is tangent of theta over 2. This is equal or greater than the area of just the sector. Right? If we just look at this area of the sector here, that is clearly less than the total area of the triangle. And what is the area of the sector? If this is theta, area of a sector is theta over 2. Theta in radians there. And then this third picture, we have again the sector, but we're going to draw a different triangle here. So we have another triangle here, where again this point was cosine theta, comma, sine theta. In other words, the height of this triangle is sine theta. The base is still 1. And the area of this triangle that I've shaded in is sine of theta times 1 divided by 2, right? Base times height divided by 2. So what we get is tangent of theta over 2 is equal or greater than theta over 2, which is equal or greater than sine of theta over 2. All right. For some angle in the first quadrant. For some theta in the first quadrant. All right. So let's do one thing here, and that is to multiply by 2 over sine of theta everywhere. All right. If we multiply by 2 over sine theta here, this becomes 1 over cosine theta is equal or greater than theta over sine theta is equal or greater than 1. Now, of course, this has an issue specifically at theta equal to 0, but we don't care what happens at theta equal to 0, because that's where we're taking the limit at. We only care about everything that happens right around that point. So we don't actually care what happens at 0. So this is true everywhere except 0, but we don't care what happens at 0. So as long as this is just true everywhere around 0, that's all that matters. All right, now let's take the reciprocal of everything, and when we do that, we have to switch the inequalities. So we actually get cosine of theta is equal or less than sine of theta over theta is equal or less than 1. Again, everywhere except for theta is equal to 0. Moreover, since cosine of theta is equal to cosine of negative theta, and sine of theta over theta is equal to sine of negative theta over negative theta, since we have that, then this inequality is true on an open interval surrounding 0, and that open interval can be negative pi over 2 to pi over 2. So these two things right here just tell us that this inequality is also true from negative pi over 2 to 0. And technically, again, this is not true at 0, which is in this interval, but we don't care what happens exactly at 0. We just need it everywhere in an open interval around 0, except potentially at 0 itself. So we have this inequality is true. And, well, what do we know? If we just think about the graph of cosine, if we just think about the graph of cosine, you should see that this limit is 1. So you can convince yourself of that just by drawing out the graph of cosine. And moreover, the limit as theta approaches 0 of a constant 1 is just 1 as well. So these two limits are the same. So the limit as theta approaches 0 of the smaller function is equal to the limit as theta approaches 0 of the bigger function. Then by the squeeze theorem, that means the limit of as theta approaches 0 of the middle function must also be 1. So by the squeeze theorem, we get what we wanted in the first place, which is that this limit is 1. All right. And that concludes our proof and the video.